Okay, so we'll pick it up now where we left off. We started to briefly consider derivatives of inverse trig functions. So let's just quickly remind ourselves, what exactly does that mean, an inverse trig function? So the way it works is that we've defined for each of the trig functions what's called an inverse function, which is called an arc function. So for example, sine to the -1 power represents what we'll call the arc sine. And it basically is the reverse of the sine. In other words, if the sine of 90 degrees is 1, that implies that the arc sine of 1 is 90 degrees. So you're basically reversing the process. With the arc sine, you're asking yourself, what angle corresponds to this sine? Anyway, so it turns out that the inverse trig functions can all be differentiated. And of course, there's a whole slew of formulas here for us. And you can see they have an interesting pattern. After a while, you start to recognize these when you see them. There's somehow always an x squared involved, 1 plus, 1 minus x squared. Usually there's something going on in the denominator. In fact, in every one of these cases, 1 or -1 is in the numerator, and either 1 plus x squared or 1 minus x squared or some function of those are in the denominator. So what we need to do is recognize these when we see them. So for example, if we're looking for the, let's say the function that we're interested in is the inverse cosecant or arc cosecant of x, then we can easily calculate its derivative by simply looking at this chart. And we just go look it up. I mean, nobody expects you to memorize that. This is the chart. But now, of course, what happens if we're looking at not x itself, but some function of x? For example, what if this had been the arc cosecant of 3x or 2x squared or something like that? Well, if that's the case, then we have a complication on our hands, which can be resolved with the chain rule. Let me show you what I mean by that. So here we go. Let's say that we're looking at the arc tangent of x squared. What is f prime of x? So if you look at the table from back here, you'll see that the derivative of the arc tangent is 1 over 1 plus x squared. So when it comes to the function of x, what's going to end up happening is we're going to end up taking the same derivative, but we'll also need g prime of x. In other words, whatever this is, we'll need to take into account its derivative. Okay, so in other words, the final result here is that the derivative of arc tangent of g of x is 1 over 1 plus g of x squared times g prime of x. All right, and so you can prove this with the chain rule, but here's the result. Again, this is the arc tangent of x squared. So what we end up with is this formula applied to g of x. So it's 1 plus x squared squared. And then here, this is g prime of x. Okay, so after a little simplification, we'll see that we'll end up with 2x over 1 plus x to the 4th power. All right, anyway, what about this next one? The arc cosine of 3x squared plus 2x. Well, let's again go back to our table and look at the derivative of the arc cosine. That's -1 over 1 minus x squared. So that means that based on the chain rule, because what you actually have here, this first term is f of g of x. If you think of this as a composite function, g, this one right here, if you think of this as a composite function, f of x is the arc cosine, and g of x as 3x squared plus 2x. Then, because we're looking at the chain rule here, f g of x prime, as you recall, is f prime of g of x times g prime of x. Okay, so therefore, f prime of g of x in this case is this term. It's exactly the same as what we have up here with the cosine, arc cosine of x, except all the x's are replaced with g of x's. And then at the end, you have g prime of x. So what you need to do is find the original function, the original derivative for arc cosine of x, and then figure out the derivative of g of x. Okay, so when you go through all those steps, again, you have this is our g of x, which implies that g prime of x, based on the power rule of 2 times 3 times x to the 2 minus 1 plus 2 times 1 times x to the 1 minus 1, or more simply 6x plus 2. Okay, so remember, the power rule tells us that if our function is k, x to the n, f prime of x is nk x to the n minus 1. So that's why the derivative of 3x squared plus 2x ultimately becomes 6x plus 2. So that's our g prime of x. So again, if you want to write this out in terms of the chain rule, and then the g prime of x is what we just determined to be 6x plus 2. So you can actually write this as the entire result. Sorry, the final result, which is actually this. You're going to have minus 1 over 1 minus, oh, I forgot to write down, g of x is 3x squared plus 2x. So you've got 3x squared plus 2x. The entire expression will be squared here. And then the g prime will be replaced with 6x plus 2. Now up here, what's happened is the 6x plus 2 is just moved to the numerator. So these are the same result, of course. So it's minus 6x plus 2 all over the square root of 1 minus 3x squared plus 2x. The entire quantity is squared. So it's always just a two-step process. Take the derivative from the chart for x, and then replace all the x's with g of x's. And then at the end, you'll multiply by g prime of x. That's really what you're doing. So like, let's see. Now this one is a bit more complicated because there's two things going on. It's a product rule, and then there's an arc sign in here. But we don't really need the chain rule this time because it's the arc sign of x. So remember our product rule. If f of x is the product of two other functions, g of x and h of x, then the f prime of x follows according to this, what you're seeing here, gx h prime of x plus h of x g prime of x. All right, that means we can think of this as g of x and h of x. Okay, well, if that's the case, then we can figure out very quickly and easily what the derivatives are. So remember, we defined g of x to be x squared, h of x is the arc sine of x, based on the power rule. If f of x is, once again, kx to the n, f prime of x is nkx to the n minus 1. And in this example, 2x, x squared rather. Remember, there's an implicit 1 here. So the derivative would be 2 times 1 times x to the 2 minus 1 equals 2 times x to the 1, or just 2x. Beautiful. Now over here, this one, we just look it up in the chart. Okay, so we can scroll back where we want, but this is the derivative of the arc sine of x. So now we apply the product rule. Okay, let me just quickly remind you that g of x is x squared. G prime of x is 2x. H of x is the arc sine of x. And then h prime of x is 1 over radical 1 minus x squared. And then here's the product rule, so we can just substitute. We have g of x, h prime of x from the table, the original function h of x, g prime of x. Now something like this, there isn't a whole lot you can really do with it. I mean, you can just leave it like this. There's no way you can realistically simplify it. Okay. Anyway, now we're going to move into something that's a little bit different. Sometimes we run into functions that are very complicated. Now, normally when we take derivatives, what we have to actually do is rewrite whatever equation it is in such a way that y is on the left-hand side of the equation and all the other terms, the x's and the constants, are on the right-hand side. And then we apply our rules. And that's normally how we approach taking derivatives. But here, sometimes we run into a problem where it isn't really easy or even possible to split up all the y's and x's and gather them onto two sides of the equation. So I'm showing you one right here. Y equals cosine xy. It's not realistic to think that we could split up this equation and have only functions of y rather on the left and x on the right. But we can still take the derivative of this function anyway. So we have to be introduced to some new rules. It's actually an extension of the chain rule, except we're going to be using Leibniz's notation here. So what is this all about? What we're going to do, let's say we have something like this. We need to know the derivative, the usual derivative, dy dx or f prime of x. So remember that f prime of x is the same thing as dy dx. All right, so here we're trying to find now you could actually with this one, you could do it the normal way, I suppose, but let's see how this implicit differentiation works. Sometimes implicit differentiation is used just because it's more straightforward, not because you couldn't do the traditional approach. But let's just see how this works. So we're going to differentiate both sides with respect to x. So you notice how we're changing the notation so that it's clear. D of all of this dx means the derivative of this expression with respect to x. Over here, same thing, d dx of 25. So you're differentiating this with respect to x. And so the rules haven't changed, but if you notice there's a y squared in here, what do we do with that? Well, clearly, this right-hand side equals 0. You're differentiating a constant. It's going to give us a 0 no matter how you look at it. So right off the bat, we know that the x squared plus y squared equals 0. Now, we can turn this around now. And differentiate each piece of this expression separately. So you recall one of the rules that we learned was that f of x plus g of x could be rewritten as either d dx f of x plus d dx g of x, or simply f prime of x plus g prime of x. And the same thing is true here. Even though this one involves a y, we're still differentiating both of these terms. Now, clearly, the derivative of x squared is just 2x from the power rule. What do we do about this y now? We're trying to differentiate y squared with respect to x. Now, this is the new part. This is something we haven't seen before. Turns out that what we're actually doing is applying the chain rule using Gottfried Leibniz's notation, and I'll show it to you in a second. We're actually going to take the derivative of y squared. We're applying the power rule here. But since y is a function of x, we also need this derivative, which could be interpreted as f prime of x. So in other words, if this had been x squared, we would have been done 2x, you're done. But because it's y, we need this derivative due to the chain rule. Okay, now I'm going to show you why in a second. So this is what makes this unique. We're differentiating a different variable with respect to y, so we need to take into account the derivative of that variable with respect to x. That wasn't necessary up here. Although technically it turns out that what we're actually doing up here if you want to be very formal about it, this is actually 2x dx dx, but this is just 1. Okay, but here it's dy dx, and so that does not just go to 1. So anyway, here is the proof of this. And again, we're using Leibniz's notation here. You might recall we wrote this out as f prime of x is the same thing as dy dx, and that can be reinterpreted as dy du, du dx. So if u is a function of y and y is a function of x, u is now a composite function. Okay. And combining that with this chain rule, oh, look what happened now. This can be written as du dy dx. So where does that get us? Okay, so remember, so what you've actually got here, let me write it again, is because it's u is a composite function of g and x, we're going to write this as du dx, which in turn can be broken up into du dy, dy du. All right, so because the function is y squared, u is y squared, that implies that du dy is 2y, or du is, actually, we don't need just du right here. What about dy du? Oh, I just realized I wrote this wrong. This should have been dy dx. That works. Okay, good. So in other words, du dy is 2y. And of course, dy dx, it is whatever it is. We don't have a separate expression for that. So du dx is the same thing as d of y squared dx. And of course, we just got through showing that du dy is 2y. And so this is the final result. Now, by the way, I want to point out that a lot of books use a slightly different notation for this, just because it's easier. Okay, you might recall somewhere along the way we mentioned that there's different ways of writing the first derivative. At prime of x dy dx, but you might and we didn't use this very much, so you might remember, I've forgotten, sorry, that y prime also means the first derivative. Okay, so that means that in this expression, when we write du dx equals 2y dy dx, what you often see written in many textbooks is they'll write it as 2y y prime. Okay, why? Just because it's simpler, but it means the same thing. Now, once that's done, like here, for example, let's go back and revisit the question that we had. Okay, so this equals 0. Now, we know that when we take the derivative of x squared with respect to x, it becomes 2x to the power rule. The chain rule tells us that this is equal to 2y dy dx. So we still ultimately are trying to solve for dy dx. That's the whole purpose of all of this. So now we're going to use some algebra. We'll subtract the 2x from both sides, and then we'll divide it out by the 2y, and we end up with minus x over y. Now, if you notice, this is not just a function of x. It's a function of x and y. So cases like this are usually best handled with the so-called implicit differentiation. Now, you can actually use this anytime you like. It's just that it's not really necessary unless you have a function where the x and y can't realistically be separated from each other. So this is often the next best approach to solving for the derivative when we have a messy expression like this. All right, now let's try another example. We'll work it through straight all the way through. And remember that chain rule. When we take the derivative of y with respect to x, we have to use the chain rule. So what about this one? Now you can see, again, this would be kind of a mess. Not impossible, but a mess to separate out the y from the x. So let's try implicit differentiation. So you're applying the derivative or taking the differential of both sides. Now, obviously, the derivative of 0 is just 0. And now I'll just subtract this one. Okay. Now I'll differentiate each one separately. And of course, I can just set them equal to, I'll move this to the dx and 10x to the right-hand side. Now, the second, this term is pretty straightforward. By the power rule, it's just 10. This is the interesting one. So let's think of this. We're going to use the product rule. And we're going to have, we'll let g of x be the first term, h of x be the second term. Now, what do we get out of that? Well, let's copy this to the next slide. So this is g of x and h of x. Now, if I take and differentiate 3x squared. Based on the power rule, remember again, might as well review it one more time. Well, by now you probably have this thing memorized. Then here we have two times 3 times x to the 2 minus 1, which is just 6x. That's the easy one. What do we do with this one? Wait a minute. It's just y. So we're going to write h prime of x simply as dy dx. Okay. So we'll copy, we'll move this to the next slide. So again, this is g of x. This is h prime of x. This is h of x. And g prime of x. That's the first term. Okay, so in other words, remember way back here, we said that this term, the derivative of the left-hand side equals the derivative of the first side, right-hand side, which is 10. So what we just calculated is set equal to 10. All right, so remember, this is where we were before we tried to take the derivative. So, and here's the result of taking that derivative. We'll move this back here so we can see it. So in other words, this derivative is this from the product rule. And this is 10 from the power rule. Okay, now I just set them equal to each other. 3x squared dy dx equals 10 minus 6xy. I multiplied, I've subtracted this from both sides to get to this point. And now remember, all I'm trying to solve for is dy dx. So a simple bit of algebra will give us our answer now. Okay, so let's move this to the next slide. And then you can see all I've done is divide both sides by 3x squared, and that's my final result. And again, you can see it's a function that contains both x's and y's. So this is often the case when we have implicit differentiation. All right, so it's a very interesting idea. You don't need it very often unless you're dealing with incredibly messy functions, but it's important to know how to deal with these cases. So now we're going to turn our attention to exponential functions, which we reviewed extensively in the beginning in chapter 1. An exponential function is one that looks something like this. And so e to the x is a classic example of this. Remember, e is a constant. So in other words, it plays the role of b in this expression. E is approximately 2.71828. We see this all the time in business applications. So what we'd like to know is, how do we take its derivative? It's a very interesting question, and it turns out to be an incredibly simple answer. The derivative of e of x is just e of x. You don't see this very often. The derivative of a function is equal to itself. That's a very rare case. Now, that raises an interesting question, though. What happens if it's not e to the x, but some function of x? Well, that, of course, changes everything. What we're going to do is see how the chain rule is applied here. You'll see it's a very straightforward result. So if f of x is e to the g of x, then the derivative is e to the g of x. But we need now g prime of x. We always, this is what really makes the chain rule interesting, that we have to take into account the derivative of this function of x that we're dealing with. So actually, if you want to be technical about it, we were doing that already, because just think of this g of x as x, then g prime of x is just 1. So you're actually technically using this chain rule here. It's just that the g prime of x is 1, so it drops out. So technically, we're always using the chain rule. It's just that you don't have to explicitly consider it if we're dealing with x instead of g of x. All right, let's look at a simple example of this. F of x is e to the 3x. That means g of x is this exponent of 3x. And by the power rule, g prime of x is 3. All right, so this is the chain rule that applies to an exponential function. So e to the g of x is just e to the 3x. G prime of x is 3. Okay. So you just end up, and usually you rewrite these. You could leave it as e to the 3x times 3, but by convention, we typically try to put the constants up front. 3e to the 3x. All right. Now, this next one takes the complexity to a slightly higher level. Imagine now we have a constant involved. Well, what we technically are actually going to do here is use the product rule and the chain rule. The chain rule will allow us to deal with this. The product rule will allow us to take into account this constant. So if you assume that g of x is x squared, g prime of x is, of course, 2x. What we're going to do is treat this as if we had two functions. Actually, we have to be careful with the notation because we don't want to use g for the same thing twice. I'll tell you what. I'll call this, let's say, k of x. No, not k, because that's usually used as a constant. I don't know, w of x, that'll do. So just for this, yeah. So, but ultimately what we're trying to do is think of this as a product rule, which means this is our g of x, and this is h of x. And of course, here's the statement of the product rule. So if g of x is 3, g prime of x is 0, h of x is e to the x squared. Now then it's the h prime of x that we have to think about. So we'll do that on the next slide. So what do we do about h prime? All right. So here's the general statement of the rule for an exponential function. So what we have here, f prime of x is e to the x squared times 2x. So going back to the original product rule, Okay, now remember we started out with, let's just quickly remind ourselves. And we determined that g of x is the 3, g prime of x is 0. H of x is e to the x squared. And then we determined just now that h prime of x is 2x e to the x squared. Okay. So when we plug in all our numbers, a 3, 2x e to the x squared plus e to the x squared times 0. Anyway, we end up with 6e to the x squared. So anyway, by the way, I just want to point out here, though, that if you notice, when we had our original case, when we started out, we had f of x is e to the 3x. Well, actually, no, there's two separate cases, but ultimately we wind up with simply a constant multiplied by the expression. Anyway, so let's try this one. Now, this one is even trickier because we have a quotient rule and the chain rule. Okay, e to the x squared over x. So to solve for e to the x squared, we'll need the chain rule. But for the entire ratio, we'll need the quotient rule. Okay, so we can think of this as g of x. And so obviously h prime of x is simply 1. G prime of x is going to be e to the g of x. Actually, let me not use that notation. It's going to be e to the x squared times 2x, as we saw earlier. Because you have the original function times g prime of x, the exponent, the derivative of the exponent. So we got everything we need. We can just plug them in. All right, here on this slide, I've summarized everything. So that means that so that we can view, okay. All right, so we have, so make some space here. All right, here we go. All right, so let's simplify this a little. So you got an x and 2x. I'll consolidate those into 2x squared, e to the x squared minus e to the x squared. all divided by x squared. But you see, we have two terms that could be combined. So we end up with x squared, e to the x squared over x squared. Wow, this is really, turned out to be very simple, surprisingly simple. Oh, wait a minute. No, what? I'm sorry. I did something wrong. I got too over ambitious here. Hold on a second. I just realized I goofed up the consolidation here. It should have been this. All right, let me try that one more time. It's e to the x squared is a common term to both of these. There we go. Now we're talking. All right, sorry. I screwed it up. Here is what we end up with. That's much better. Okay. For a second, I was trying to combine two things that I shouldn't have. So it's e to the x squared. We can factor that out. 2x squared minus 1 all over x squared. All right. Now, since we're discussing derivatives of exponential functions, it makes sense that we're going to now turn our attention to logarithmic functions. They go together. They're inverses of each other. So it makes sense, or at least natural logs and exponentials, e to the x, are inverses. So they're always going to be discussed at the same time. So now let's take a look at logarithmic functions. And we're going to focus our attention. We're going to not exactly ignore the other logs, but most of our attention will be based on natural logs. So, but we will see how the results change when we have the other logs. So as long as x is positive, if f of x equals log x, f prime of x is simply 1 over x. Well, that's kind of interesting. And of course, you can see why x can't be 0. Now, what do we do about functions of x? In other words, what if instead we had something like this? Well, as you can probably guess, we're going to use the chain rule. And you could probably even imagine what it's going to look like. It's what we started out with. Remember, f prime of x, or simply x, is just 1 over x. So for f prime of g of x, log g of x, that is, it'll be 1 over g of x times g prime of x, or we often see it consolidated into g prime of x over g of x. All right, so let's take a look at a quick example. What if we have f of x is a function, it's a log of a polynomial. Here we are. So this is g of x. And based on the power rule, we end up with g prime of x is 3x squared plus 3. So literally, all you have to do is put that derivative in the numerator and the original function in the denominator, and you're all done. Unless there's some way to simplify this, that's it. Now this one, now sometime, by the way, with these cases, before you start trying to do a horribly complicated derivative, thanks to the properties of logarithms, sometimes we can make things a little easier for ourselves. And here's a good example of that. We have the log of, oh my God, look at this. But we remember the log of any base of xy is the log of x plus the log of y. And furthermore, the log of x over y is log x minus log y. We're going to put that to good use here, okay? Because if we try to solve this the way it is, we're going to have a mess. But we're not going to go down that path. We're going to simplify it as follows. Okay, so in other words, you've got a product in the numerator. So we can rewrite that as log x squared plus log sine x minus log 2x plus 1. Now, each one of these could be considered log of g of x. Okay. It's a different g of x in each case. We're still going to write it as log g of x. Just so you can see that g prime of x here is 2x. And remember, the derivative of the sine is the cosine of x. And here we simply end up with 2. So in each of these cases, we have the derivative in the numerator. And in the denominator, we have the original function. So I think you'll agree this is a lot quicker. If we'd done it the other way, suppose we didn't bother to use these log properties, what we would have needed, this would have been our g of x. The g prime of x would have been a bit of a nightmare. It would have required the quotient rule. So I think you'll agree that in this case, at least, we definitely sped things up by using the properties of logs. And so we end up with a not too terribly complicated result. They would have been the same numbers, but I mean the same result, but I think you'll agree this is a lot easier. And here we're going to do the same thing, except this time, now remember, with a log of any base of x to the n power, oh, that's right. Yes, so this can be rewritten. So instead of dealing with this exponent, so g of x, g prime of x would have been very complicated here. Instead, we reduce it very simply to 5 times log 3x plus 2. And now this is easy. Okay, so quickly, let me remind you one more time. This was originally 5 times the log of 3x plus 2. Think of this as g of x. And so therefore g prime of x is simply 3 based on the power rule. And remember too, so here's our g prime of x, here's our g of x. And then of course the 5 is still there, don't lose the 5. So you end up with 15 over 3x plus 2. And that's it, you're done. If you'd left it like this, you would have gotten a very complex chain rule problem. Like this, I mean, I think you'll agree this was a lot quicker. All right, now, I did mention before that we might sometimes find ourselves dealing with logs that are not natural logs. The others, what do we do then? Well, the rules are slightly different then. So if we have something like this, remember, if f of x is log x, then f prime of x is 1 over x. Now, this is the general rule. This applies for any base b. So instead of 1 over x, we have 1 over x log b. Now, even here, we're actually using this rule because natural log is log base e, which implies that f prime of x is 1 over x natural log of e, but that's just 1. So what this one on the top is a special case of this rule that we're seeing now. Okay, so just be aware that when it's natural log, yes, the derivative is 1 over x, but this is just a special case of the general rule for the derivative of a logarithm. We just don't have to bother here because it just goes to 1. Now, of course, we then have to see what happens when we have the log of a function of x. Okay, so quick reminder, when f of x was log g of x, then f prime of x turned out to be g prime of x over g of x. Well, the same thing is, you can see here, when we have log b, we need to include this natural log term. But again, if that base is e, um, whoops, natural log e, which is just 1. Okay, so, and also, here's another interesting case. What if you have b raised to the x power? This is an interesting case. It turns out the derivative is b raised to the x power times log b. So up to this point, we haven't run into this because here x is the exponent. That's what separates this case from the others. Okay, that wasn't true before. And now, of course, what about the case where it's b to the g of x? What do we do then? Ooh, okay. So again, remember, if f of x is b to the x, then f prime of x is b to the x log b. If instead it's b to the g of x, then based on the chain rule, it's b to the g prime of x. And so you notice the log b is here. This is the new part. In fact, maybe what we should do is write this as like this, so you can see the comparison between the two cases. Oh my God. Is this making your head spin? Yes. Well, after a while, when we have enough practice, you'll see, this isn't so bad. But what we're really seeing here is techniques for dealing with more complicated situations, specifically when there are logs or exponentials involved. All right. How about this case? So let's keep this formula in mind. So this is log 3 of x. Oh, actually, for this one, we need this. Here we go. Hold on. Yeah, actually, that's the job. That's a job for this formula here, not this one. So if f of x is log b of x, then the derivative is 1 over x log b. So here, because it's log 3, we have 1 over x log 3, and it's that simple. If this had been natural log of x, then the derivative would have been 1 over x. This extra piece is required because it's not the natural log. And then, of course, if we have a function of g, function of x, then f prime of x, let's just go copy that formula. There we go. All right, so of course, that's what we have here. So our base is 5, and g of x is 2x to the fourth minus 3x squared. So based on the power rule, oh, there they are. G prime of x is this expression. So now we just have to plug everything in. G prime, here's G. And then we need here natural log of 5. Ooh. All right, and then one more quick example. Now, this is that case. Remember, oh, there's 2 more examples. So here b is 3. So we end up with 3 to the x log 3. All right, and then lastly, we have this one. So all right. So in this case, b is 3. The exponent is 2x cubed. Based on the power rule, we have 6x squared. We plug everything in. This is b, the original b of g to the g of x power. And that's it. All right, so this is, I called it the appendix. It's not really an appendix. This is just the more complex material towards the end of the chapter. But since we're done with this, we're ready for 4. And 4 basically is starting to take us into more applied aspects of derivatives. We're not just focused on the rules here. We're looking at different applications. And so among the most important ones here are this one right here, maxima and minima. We often use calculus to try to find the maximum value of a function or the minimum value of a function. We see this a lot in economics. And we have some other important results in here too, but for applied fields, this is going to prove to be critically important. We'll see this all the time as we go forward more into calculus, Calc 2, even Calc 3, and specifically applications like economics, which is heavily based on this. But anyway, so that's something to look forward to. So we're done with 3 appendix, and so I will see you next time.